Hi everybody, we're back at it again! Another set of notes to complete here. So we got two things on the docket today. We got Chapter 6, which is sampling distributions and the central limit theorem. That's a very important concept. And then we got an introduction to hypothesis testing. So let's take it away. Well, what we're doing today, what are we doing today? Like I said, we're going to be looking at the central limit theorem. So we start with talking about the sampling distribution of the sample mean. Now stick with me because this is pretty tricky and you may want to actually replay this a couple times. So the idea is that sampling is hard. We begin to deal with the difference between a sample statistic and then the true population statistic. If you think about it, different samples are going to provide you with different sample statistics. Like if you take a sample of 10 people's height in Brandon, you're going to get a mean, median, and a standard deviation. If you take a different 10 people, then you're going to get a different mean and a different median and a different standard deviation. So the general idea is that the larger your sample is, the smaller the error is going to be. But it gets more complicated. It's always more complicated. So the sampling distribution is the sample that you've collected. Okay, so sampling distribution is the sample you've collected, while the sampling distribution is the theoretical sample of all samples you could have sampled. So think of this as the matrix blue or red pill. So the sample distribution, that's what you get. So you sample your 10 people for height, that's what you got. But the sample of all samples, which is the sampling distribution, that's like the other side. That's like the theoretical sample of everything you could have gotten, or the population. Okay, so the sampling distribution of the sample proportion. We're going to adjust our formulas a little bit to account for what we call standard error, right? So if you got, everybody in Brandon and you how many people you need to sample to get the true population statistic for height is sort of the idea. You probably won't be able to sample that many people, so it's kind of generally understood that if you take a sample, there's something called an error in it. And that error has something to do with the true randomness of your sample. The more random your sample is, the less error you're going to have. Well, this is the central limit theorem. The value of the sample mean will change from one sample of a certain size, n, to another sample of the same size, n. Well, that just makes sense, right? If you sample 10 people for height in Brandon, probably not very realistic, but if you start sampling 1 or 2% of the total population of Brandon, then you might be getting closer. So, therefore, the sample mean is a random variable, and we are interested in its probability distribution in order to make inferences. The probability distribution of the sample mean is called the sampling distribution. We are interested in studying the sampling distribution of the sample means. Remember, the sample mean is what you get. The sampling distribution is the theoretical sample of all samples. Let me flip my page here. So, a couple definitions that could be useful for theory and stuff like that. Sampling distribution, the probability distribution obtained by using random samples of a specific size. So, random samples of a specific size from a population. Notice I'm using a nice purple pen today. Sampling error. So this is the actual difference between the sampling measure and the corresponding population measure due to the fact that samples are not a perfect representation of the population. All right. For example, we're going to go really far with this example. So a box contains 3 tags labeled 1, 3, and 5. What would be the population mean and the standard deviation? Well, let's see. The population mean, it's going to kind of do it over here. Well, we just got the 3 tags, 1 plus 3 plus 5. And then how many tags are there? Well, there's 3 tags. So add them up, you get 9 divided by 3. And 9 divided by 3 is 3. So the population mean is 3. And the standard deviation, well, we can do that over here. So we're going to do the square root. My line is not very straight. So remember that it's the square root of every x minus the mean squared. Okay, so we're going to go the first x minus the mean squared plus the next x value minus the mean squared plus the next x value minus the mean squared divided by, now we're going to use the population formula because this is the population. It's everything that's in the bag, so we're going to divide by 3. By the way, I thought it might be good to just show you the formula, just to remind you, for standard deviation, if it is for the population right here, it's the sum of every xi minus x bar squared divided by n. Pro tip. Okay, so I'll give you a moment, pause the video, type that in on your calculator. And once you've unpaused here, you will get 1.633. Okay, so these are the actual population mean and population standard deviation because we're going to say that this is everything in this particular category of tags that we're interested in, or these 3 tags. Okay. So if we randomly select a tag with replacement and let x be the number selected on the tag, then each tag will have the same probability of being selected. Now, to demonstrate the central limit theorem and what it means for us, I'm going to use this example as sort of a way to show you why the central limit theorem works. So to do that, we're going to do all the possible sample sizes of 2, of n equal 2. Remember, we're doing this with replacement. So that means that when you remove a tag, you look at the number, and then you put the tag back in so that they all have the same probability of being selected. Okay? So, next slide here. Now, here we go. We're going to find the mean and standard deviation of the sample means. So we want to study the sampling distribution of the sample mean for all possible sample sizes of size n equal 2. We're going to find the mean of means and the standard deviation from the table below. So this is every single possible scenario that can happen if we draw 2 tags with replacement. This is everything. So this means that this is the population, right? So you get a 1, 1, or a 1, 3, and a 1, 5, or you get a 3, 1, a 3, 3, a 3, 5, or 5, 1, 5, 3, 5, 5. Okay? And I've already gone ahead and calculated the sample mean for each scenario. So just as an example, for this first one, if you go 1 plus 1 divided by 2, you're going to get 2 divided by 2 and 1. So that's the sample mean. Okay, now we're going to find the mean of means. So we're going to use mu, because it is the population. And we're going to go, so mu of all the different means, so mu of x bar. So let's add them all up. We're going to go 1 plus 2 plus 3 plus 2 plus 3 plus 3 plus 4 plus 3 plus 4 plus 5. And there are 9 different cases. So add them all up, divide by 9. You can pause the video here if you like. And you're going to get 3. Let's compare this to what we had before. So if this is indeed the entire population that we have, we calculated a population mean of 3 before, and we did a sample of all samples for taking 2 tags out, and we got 3. So we didn't break statistics yet. Now, where does statistics sort of break down? Well, let's go find the population, or the standard deviation for this population. Okay? So what we're going to do is we're going to use the regular formula that I showed you before, just to be sure that we're all clear on which one it is. We're going to be using this one here, and we're doing the population version of it because we have the population in front of us. So here we go. We are going to be taking every mean and subtracting the population mean and squaring it. We're going to do the square root of the whole thing. Now, I'm totally going to run out of room here, so what I'm going to do is make my big square root sign, okay? And I'm just going to try to fit everything in here. So we're going to go 1 minus the mean of 3 squared plus the next one, 2 minus the mean squared plus the next one, 3 minus the mean squared, and then the next one. So plus 2 minus the mean squared plus, and I'll squeeze another one in here. We're on this one, 3 minus the mean squared plus, now I'm just going to go on the next line. So I'm just going to kind of go like this. 4 minus the mean squared plus 3 minus the mean squared plus 4 minus the mean squared plus, last one, 5 minus the mean squared. Okay, I'm going to divide all of this, and I know this isn't ideal, but I just ran out of room, divide by n, which is 9. So we're going to be doing the square root of all this stuff. So I'd suggest pause the video at this point, calculate this out, and make sure you get the same answer as me. So, actually, I do have a little bit of intermediate work here. Oh no. Oh no. Apparently that button. Okay. Alright, so I got some intermediate work, so you should get 4 plus 1 plus 0 plus 1 plus 0 plus 1 plus 0 plus 1 plus 4. Still divided by 9. Now, equals, so you're going to get basically the square root of 12 over 9. And drum roll, please, because we have found the population standard deviation to be 1.1547. Huh. Now, let's compare this to what we had before. The population standard deviation should be 1.633. What the heck is going on? That can't possibly be right. I can guarantee you we did all the work right, but there's something wrong here. We should get the same number. We should get the same number because this is the entire population of all the sample sizes of n equal 2. So when we calculate our standard deviation, we should get the same standard deviation for the population as we got before. But it's just not happening for us. So that's a problem. Now, so we can just say it does not match. So this does not equal. Hold on. Hey, what happened to my pen? Oh, Jesus Christ. Okay, so this does not equal what we got before, which was 1.63299. Okay, so what's going on here? They don't equal each other. Well, this is the central limit theorem, or at least where it comes in. Now, somebody figured this out. But if we take that population standard deviation and we divide it by the square root of n, then we will actually get this number here. So let's try it out. So if we take this 1.63299, we divide it by the square root of, what was the sample size, 2. Then if you type that into your calculator, try it out, you will get 1.1547. Perfect. Yay. So we didn't break statistics, okay? So what does this mean for us? Because this is sort of a weird thing, right? Like the mean works fine, right? We had the sample of all samples for size 2 tags. And when we did this, all the different sample means and added them all up, we indeed got the population sample mean. When we did it for standard deviation, though, it didn't work. We got the different standard deviation. But if we took the true standard deviation and divided by the square root of the sample size, then we got the sample standard deviation. Interesting. Let's write that down. Let it sink in a bit. So we find that the mean of the sample means equals the population mean. Right? That's what we found. So we can say that the sample mean is an unbiased estimator of the actual parameter. That's good. But we found that the standard deviation of the sample means equals the population standard deviation divided by the square root of n. So that is very important. You should highlight that. So the standard deviation, therefore, must be a biased estimator of the parameter, and that's called the standard error of the mean. That's what the standard deviation does for us. It gives us a standard error on the mean, right? The height is 2 meters plus or minus some error, right? It measures the extent to which sample means can be expected to vary due to chance. And the standard error increases when the standard deviation increases. So bigger standard deviation means you have a bigger standard error, and it decreases as the sample size n increases. That makes sense, right? I mean, we already knew that. If you get a bigger sample size, you'll likely have a less standard error. This is a big concept. It took me, and I'm not sure if I 100% get it, but it took me years and years and years for this to really sink in. So don't feel bad if you're looking at this and being like, what just happened? You can certainly watch it a few more times, but it really does take a lot of questions, at least I'd say for most people. Maybe some people understand it perfectly the first time. It takes quite a while to really understand it. And it is one of the trickiest things in all of statistics that I know is the central limit theorem. So, the most important theorem of statistics, the central limit theorem, describes the sampling distribution of the sample mean, right? So you get all these different samples of the actual mean of a population, and they all land in a different place. And what the central limit theorem does is it sort of figures it out for us. So it is used every time we need to make inferences about the mean mu of a population using data from random samples. So let X represent data values from a population with a mean of mu and a standard deviation of sigma. Let X bar represent the sampling distribution of the sample means for all sample sizes of n. X bar is a random variable with the following properties. Well, the mean of sample means is this, right? We found that when we did the mean of all the sample means, we got the population mean. The standard deviation of sample means is this. Remember, this is the actual population one divided by the square root of n. So the sample means will be approximately normal when n is large. Now, in statistics, it's generally agreed that n is large if n is greater than or equal to 30 in general. It depends, but in general, that's the case. The larger the value of n, the closer the distribution will be to normality. Remember, normality means to the normal distribution, okay? Note, we did not require the original population X to be normal or even continuous. If the population X is normal or approximately normal, then the sample means will be normal for all values of n. And that's pretty neat. So basically what it's saying there is the central limit theorem helps us normalize data that is close to normal or not even necessarily normal, helps us normalize it. So that's a pretty powerful theorem. It lets us do a lot of things that we normally wouldn't be able to find probability distributions for. So if you can appreciate that, then you're a lucky person. So beware. So how do we know? Like now we're going to have our typical Z table question. So what does this mean for you really is what I'm getting at here. So you have this Z score that we've been doing now for a little while. How do I know when it's a regular Z score question and a central limit theorem question? Well, a little bit you need, if you understand the central limit theorem, you'll see it, but I remember when I was a student, that's actually pretty hard because you're just learning this stuff. And this is a very complicated topic, actually. So yeah, when a question's asking for X less than or greater than a certain value, it's probably just a regular Z table question. Okay, but how do you know when it needs the central limit theorem? Well, the question's usually going to talk about a sample, or more likely the question will maybe speak to some mean and some standard deviation, and then start asking you about a specific situation that involves a sample. Okay, when that's the case, it'll be a central limit theorem question, and this is how we modify the Z-score formula for that. So all that's changed here is that because we know that we may not actually have the correct value for the standard deviation, we're going to use the standard deviation divided by the square root of n, because the central limit theorem shows us that actually helps correct it. Okay, so let's go ahead and do some examples. Just a couple of pictures of the effective sample size before we get there. So small sample size, as soon as you start getting bigger, once you get to n equal 30, you really start getting something that looks more like a normal distribution. Okay, so our first central limit theorem example, here we go. So, a freight elevator transports a maximum of 9,800 pounds. Suppose a load of cargo containing 49 boxes is to be transported. It was found that historically, boxes of this type of cargo follow a distribution with a mean of 205 pounds and a standard deviation of 15 pounds. What is the probability that all 49 boxes can be safely loaded onto the elevator? Okay, so the first thing I want to focus on is how do we know this is a central limit theorem question? Because remember, you're going to get this buried in a midterm or an exam, and some of them might be non-CLT questions and some of them will be. So, a couple things. A lot of students like to just look and say, oh, well, you know, they said 49 boxes, and whenever there's an n value in the question, it's always central limit theorem. Wrong. That's not the case. The problem with this question is it doesn't actually say that this is a normal distribution. And if it doesn't say it's a normal distribution, you must use the central limit theorem. Because remember, the central limit theorem helps normalize the data. So that's one reason why it's a central limit theorem question. So I'm going to write it up here just to really let it sink in. Does not actually say that it's normal, either normally distributed or normal distribution. Okay? So that's a really good reason for this particular question. A second thing is that the question as it's given, it's not really giving us an X value to test here, right? So we know that it's going to be some sort of Z-score formula question. And the question is it this one or is it this one? X bar minus the mean divided by the standard deviation divided by square root of n, right? So this is central limit theorem and this is non-central limit theorem. Well, they didn't actually give us an X value, so it means that we need to go find the mean, and that's why they've told us that there's 49 boxes and they've given us this average weight. So there you have it. So we can go find the mean, X bar. So it says that normally there's 9,800 pounds is the max, and we're going to divide by 49. We're going to get our mean box of 200. Okay, so if we have 49 boxes and the max weight is 9,800 pounds, then on average the boxes need to weigh 200 pounds. Then we can go ahead and use the central limit theorem formula, this one here. I just want to show you on the formula sheet because this week we have an updated one. Right here in continuous random variables, there's the central limit theorem down here. So there's the standard error, and then there's the new Z-score formula that we will be using if it's a central limit theorem question. So here we go. We can go ahead and we can pop everything in here. So the mean is 200, and we can subtract. Now, the population mean, it says that normally the boxes are 205 pounds. So that's going to be mu 205 pounds, and I didn't write down the standard deviation. It says it's 15. So we can go subtract mu, which is 205, divided by the standard deviation, so 15, divided by the square root of n. There we go. Now when we get our Z-score, go ahead, type it in on your calculator, you're going to get negative 2.33. Now, it's very important for this question that maybe we draw the picture because we need to sort of think about, well, which side of this table are we looking for? So what's the probability that all 49 boxes can be safely loaded in the elevator? So here's the mean. We just got a Z-score when we plugged in the sample mean of 200. We got a Z-score of negative 2.33. So we're on this side of the table somewhere. Now, we want all boxes to be safely loaded, so we're going to be looking less than this number, right? If we're more, then we're gonna be over the limit of 9,800 pounds when you have all the boxes on there. So we just want to find what that Z-score is right here. So you can bring up your Z-score table. And where is my Z-score table? There it is. And we're going to look up negative 2.33. So negative 2.3, and then go over to this column. We get 0.0099. Neat. So probability that Z is less than negative 2.33 equals 0.0099. There you go. So what's the probability that all 49 boxes can be safely loaded in the elevator? Basically 1%. we multiply by 100, or you can leave your answer like this. Does that make sense? Well, let's see. If the mean is 205 and there's 49 boxes, if you go 205 times 49, you get 10,045. Okay, so that means that, yeah, probably, if that's usually what the boxes are like, and there's 49 of them, then we're likely going to be over. So this kind of seems to make sense. When possible, it's good to just kind of double check and see if your answer makes sense. Next question. This is another central limit theorem question. That's going to be important that you guys try the homework, because you're going to get some more central limit theorem questions in there. So this one, the number of tickets purchased by a student standing in line for a UFC match has a distribution with a mean of 2.4 tickets and a standard deviation of 2. So we can go ahead and we can write that down right away. So it's a mean of 2.4 and a standard deviation of 2.0. A few hours before the match, there are 100 students in a line. Only 250 tickets remain. What's the probability that all 100 will be able to purchase the tickets they desire? Well, let's see. Again, don't fall into the trap of just being like, oh, they gave an n value in the question and it's a z-score question, so it has to be central limit theorem. That's not the case. I can give you questions where I give you an n value and it's not a central limit theorem question. So just be careful of that. How do we know that it's a central limit theorem question? Well, once again, I think one of the really good indicators is, does it say anywhere in here that this mean and the standard deviation belong to a normal distribution? The answer is no. So again, it does not say anywhere in here that this data set is normally distributed. Okay, so that's a big giveaway in this case. Another thing is that we can't actually, if we were going to use this formula, so if I thought it was a regular z-score question, it doesn't actually say anywhere what the x value is, right? They gave me the population mean, which I need right here, and it gave me the standard deviation. It's like, well, what do I use for x? Generally, when that's the case, and it's not this kind of question, it's a central limit theorem question, and we're going to be calculating an average for x based on information in the question. So in this particular question, we go find our x bar. And how would we find it? Well, there's 250 tickets left. And there's 100 people in the line. So on average, we can get 2.5 tickets per person. That's what there would be on average if everybody got the same. Okay, so now, will everybody be able to purchase the tickets they desire? Well, that would be asking for the probability that x is less than or equal to, what was our mean? 2.5. Right? On average, everybody would have to purchase less than that for everybody to get the tickets they desire. Because look at the population mean, right? Tricky. That is tricky. It seems easy on the surface, but I think that's really tricky. So it definitely might pay off to do this question more than once. So we can use the central limit theorem. We got our x bar of 2.5, and we're going to subtract the mean of 2.4. And then divide by the standard deviation, which they said was 2, divided by the square root of n to help normalize the data. And we're going to get a z-score of, go ahead, type it in on a calculator, and get 0.5. Okay, so draw your normal distribution. Whee! There you go. And here is the mean. Now, because we're looking at an x bar of 2.5, we know that our z-score is going to land over here somewhere, so that's z equals 0.5. Remember, the mean is a z-score of 0. And are we looking to the left or to the right? Well, remember that the direction this points is the direction you're looking for. So we're looking for the area of the curve to the left of that z-score. Okay, so that's what the table gives us. So go ahead and bring up your z table here. Look at 0.50, you get 0.6915. Don't forget to write it out the proper way. So the probability that z is less than or equal to 0.5 is equal to the probability that x is less than or equal to 2.5. And when you go figure that out, we got 0.6915 on the table. So there's a 69.15% chance that everybody is going to be able to get the tickets that they desire based on that distribution. Wonderful. Okay, and now we get to a topic change here. So that's the central limit theorem. Now we're going to look at hypothesis testing. So here we go. Next week we'll continue with hypothesis testing. Basically, the rest of our course is going to be hypothesis testing. Now, it's a brand new topic that we've never looked at before. So today we're just going to be looking at basically these first two things. So what is hypothesis testing? What are null and alternative hypotheses? And what's an alpha value? So we'll do that. And then we're going to be looking at single sample tests of a population mean. And if you look at your formula sheet here, again, I kind of update it week by week as we do stuff so it doesn't get too crazy. So we're looking at this box right here. So one sample hypothesis test for mean. And I believe we also do for proportion as well. Okay, so this stuff actually will be the second half of that next week. Okay. So, what is a hypothesis test? Well, hypothesis testing tells us the likelihood that a probability is true. Now, everything we do in stats is about probabilities. So there you go. We can use it to tell whether a sample statistic is actually different than an accepted population statistic. We're always interested in that, right? Because it's hard to get population statistics. We get population statistics after years and years and years of data. Usually, like I know in biology and things like that. Same thing in business. And then you start getting, then you start drawing samples to be testing things to see if you actually have a difference from the actual population. Whenever a company makes a claim that is statistically valid, they would have performed a hypothesis test, where we can either accept or reject the status quo, which is called the null hypothesis. We generally assume that the alternative claim, which is the alternative hypothesis, is false. And then we show the likelihood that the null hypothesis is not true. And if we can show this, then the alternative hypothesis may be true depending on the alpha value. So what am I saying here? The null hypothesis is sort of the status quo. So depending on whatever the question is, it is what's generally accepted to be true. The thing that you're trying to show is the alternative hypothesis. So there you have it. On to the next slide. So the null hypothesis we denote by using HO. That's how you say it. HO, that's how you write it. That's how you say it. And it's a statement of the basic proposition being tested. Just keep in mind the statement generally represents the status quo, like I said before, and is not rejected unless there's a convincing sample evidence that it is false. The alternative or research hypothesis, denoted HA, is an alternative to the null hypothesis, and that statement is only going to be accepted if there's convincing sample evidence that is true. What kind of tests can we do? Well, we can do one-sided greater than tests. We usually call these right-tailed tests. I'll refer to them very often as right-tailed tests. And the hypotheses look like this. We say that HO is that the population mean is less than or equal to the sample mean, or the alternative that the population mean is greater than the sample mean. So it's a one-sided right-tailed test because the sign is pointing to the right. The greater than sign points to the right. That's how you should remember. The one-sided less than alternative tests are called left-tail tests. And what are you going to notice? Well, the null hypothesis is that the mean is greater than the sample mean, and the alternative is less than, so the population mean is less than the sample mean. So again, this sign points to the left, that's how you know it's a left-tailed test. Now you can also have a two-sided test, where you'll generally see the words not equal to in the question, and we call that a two-tailed test. And we write that like this, where the HO is that they actually equal each other, and the HA is that the mean does not equal the sample mean. What kinds of decisions can we make? Well, as a result of testing HO versus HA, you'll have to decide either of the following decisions for the null hypothesis. So basically, it's pretty simple actually. You either do not reject HO, okay, or you reject HO, okay? What statistical tests can we use to do hypothesis testing? Well, good news is that in order to test whether HO versus HA, we need to use a test statistic. So because we're talking about normal distributions, the good news is we're very familiar with this formula. It is this one right here. Does it look familiar? That's our z-score formula. And actually, because we're talking about the mean of means, guess what? We actually use, because we want to make sure that we're normalizing our data if it's not already normal, we actually use this one right here. So it's like the central limit theorem formula. Ain't that neat? Right, where mu o is the given value or the hypothesized mean, often claimed to be true, and x bar is the mean of the sample. Standard deviation is known in this case, so you must know the standard deviation in order to do it. There are tests that we can run if we don't know the standard deviation of the population, and we'll cover those in future weeks. So the population tested is also large, so as long as it's greater than 30, so we know our population follows a normal distribution. Remember, that's what I was talking about before, that once you start having a sufficiently big sample size, then you can start to be more and more sure that you have a normal distribution. So next week we'll be looking at, these cases right here where we don't know the standard deviation. What's this alpha value? So this is the alpha value, and this is the symbol for it. It actually kind of looks like a fish. This is the statistical threshold. So the statistical threshold we were testing your claim against. It represents the probability of being incorrect. Okay, so basically in most industries, business included, an alpha value of 0.05 or a 5% chance of being incorrect is sort of like the industry standard. You'll see it in the paper sometimes when they quote like a study, they'll be like, 19 out of 20 times. So basically, there's only a 5% chance of being incorrect. The smaller this is, though, the better. So 5% is the minimum, but if you can get closer to 1%, then that'd be really good. All right. If we are incorrect, what can happen? Well, this is a little bit of theory stuff before we actually start doing questions. You can have type 1 and type 2 errors. So if you reject the null hypothesis when it's actually true, so when it is true, so if you reject it and it is actually true, that's a type 1 error. Okay? Alpha is the probability of making a type 1 error. So when we use an alpha value of 5%, we're saying, hey, there's a 5% chance that we're going to make a type 1 error, rejecting the HO when it's actually true. A type 2 error is the opposite. So it's failing to reject HO when it's actually false. And this could just it's just for your general understanding, and it could come up in a theory question. So I made a little table here of all the different scenarios. We call this beta, so this symbol here is beta. Beta is the probability of making a type 2 error. 1 minus beta is the probability of not making a type 2 error. Not super important, just thought I would throw it in there. I'm never going to ask you about this, is what I'm saying right now. Now, just know that there's type 1 errors, where you're rejecting HO when it's true, and a type 2 error is failing to reject HO with a null hypothesis when it's actually false. Okay, hypothesis testing are questions that are pretty involved. There's several steps, 5 or 6 steps, 5 or 6 things you got to do. So I kind of wrote it in a list here. So the first thing you need to do is state the null and alternative hypotheses. You must do this. If you don't do this, you're going to lose those marks. Then you need to specify the significance level of alpha and calculate what we call the rejection rule, which is the probability of being incorrect. And this is based on the normal distribution for that data set. Okay, so if we're doing a right tail test, you got to figure out what area over here and what's the z-score threshold to get there. Okay, then we calculate the value of the test statistic, so we'll be using the central limit theorem formula for that. Then you need to decide whether to reject HO by using that test statistic and looking at your rejection region. And then you interpret the statistical results in managerial terms. That's something from your textbook that I stole. And assess their practical importance. So step 5 is basically saying, can you say this in English? Okay, so you ran all these numbers and you have all these symbols. What does this actually mean for the particular scenario you're looking at? So you must have all these 5 steps or you're going to lose marks. I'm telling you now. Okay. So, here we go. Here's an example. So what I'm going to do is I'm going to do an example of a greater than test, and I'm going to do an example of, I think, a does not equal test. Let me just look ahead here. They're a lot of pages long. So we'll do, greater than, we'll do a less than, and I believe, yes, I also do a not equal to. So I do all 3 cases so that you can see them. These are questions that you're going to find in the homework. They're long questions, so important that you try them out. Remember, I give you the minimum amount of homework possible in order for you to succeed. So it's important that you do them all and that you do them a few times. So a company wishes to test their new 100-liter trash bag, which is thinner and requires less plastic than their current 100-liter trash bag. They test 40 of the new bags and find the breaking load to be 25.575 kilograms with a standard deviation of 1.65 kilograms. At the 5% level, can the company make the claim that their new trash bag is stronger than the old one, which has a breaking load of 25 kilograms? Perfect. So, a couple things to note in here. You might have to read the question a few times. There's a lot of things given in the question. And you'll know when you have a hypothesis testing question because you're gonna get the alpha value in the question. So when they say at the 5% level, your alpha value is 5%. Okay, so the good news is if it's hypothesis testing, you'll know. The bad news is we do so many different kinds of hypothesis testing that the challenge will be, which one is it? Okay, so let's go ahead to the next slide and see what we write for HO and HA. So I've tried to set this up in a way that's as streamlined as possible. When you're showing me your work for a hypothesis testing question, you'll have to do all these steps, but in our notes I have them all laid out for us. So first step was state the null and alternative hypothesis. So I'm just going to point out that on the formula sheet, I have all the possibilities here for you. I actually recommend that you start with your alternative hypothesis because it's a little bit easier to see. There's only the 3 scenarios for the alternative hypothesis, and you can get that pretty easily from the question. So like I said, you're either going to have a two-tailed test where you're testing that it's not equal to the accepted value, or you're going to have the greater than test, right? This is the right-tailed test. Okay, that whatever statistic you're testing, right, is that the accepted mean is greater than the one you're testing, or that the accepted mean is less than. In this particular question, they're trying to get us to test. Let's see. It says which has the old breaking load is 25 kilograms. They think that for their new bag, it's greater than 25, right? They're claiming the new bag is thinner and it has a 25.57 kilogram breaking load. So your alternative hypothesis is that mu is greater than 25. There. That's how I know it's a right-tailed test, right? Because it's pointing to the right and it's a greater than question, like I said. So what's the null hypothesis? Well, the null hypothesis is that mu equals 25. Or you can say mu is less than or equal to 25. Generally, I like this better. So you do your alternative first, and then whatever sign goes here is the opposite one. So if it's greater than here, it's going to be less than or equal to. Okay? Either one would be acceptable. Specify the significance level alpha. Well, it says in the question that is 5%, so we're just going to write it as a decimal right there. Now, we're going to determine the rejection rule for deciding whether or not to reject HO. So the probability alpha is the area in the right-hand tail of the standard normal curve. That's in this case because we're doing a right-tailed test. That's why it's called right-tailed. So if you draw the picture, our rejection region is over here where we have 5% of the curve, and we're looking for what is that z-score that's going to give us that value. Okay, so if it's over here, we're going to reject HO. If our z-score falls anywhere else over here, we're going to accept HO. Okay, so that's what all this says. Reject HO in favor of HA if the test statistic Z is greater than the rejection point Z alpha. This is, we're going to find what this Z alpha point is here. So how do we do it? Well, you need to find so that you have 5% here. Now remember, if you're in the middle, it's 50%. So what percentage would be to the left if 5% is to the right? Well, we're looking for the z-score that gives us 95% on our table. Let that sink in for a second. Our z-score table gives us the area to the left. So if we have 5% here, we have 95% here. So let's go find it on the table. So now we're doing a reverse lookup. And where is it here? No, we don't have exactly 95%. We do have 94.95 and 95.05, which are exactly 5.005 units from 95. So we're going to do the average. So we're at 1.64 and 1.65. So if you do the average, you're going to get 1.645. So that's this magic value here, Z equals 1.645. So in the trash bag case, the rejection rule is to reject HO if the calculated test statistic is Z is greater than 1.645. All right, step 3. Step 3 is calculate the actual Z statistic. So we're going to use the central limit theorem formula. Oops, I lost my draw a touch there. Okay, so Z equals x bar minus the mean divided by standard deviation divided by square root of n. Now we can plug in the numbers for this. So from the question, if you go back and look, the x bar value is 25.575. That's the value we are testing. And the accepted mean for the old bag is 25 divided by standard deviation of 1.65 divided by square root of n. Now, there was 40 trash bags that were tested. So when you go and calculate that, you get 2.20. Now, it's very important that you actually draw a picture for hypothesis testing. It's one of the best things you can do because it helps you figure it out. So remember, this is the rejection region. So we reject HO. This was the Z value that we looked up when it's 1.645. So on this side, we accept HO over here. So you need to write if Z is greater than Z alpha or Z is greater than 1.645, then reject HO. Okay, you must write this because it's showing me your logic, showing me that you understand. Now, what is the Z statistic we calculated? So we got a Z statistic of 2.2. I like the picture because it helps me figure out where does this fit. Am I in this region or am I in this region? Well, 2.2 is greater than here, so I'm somewhere over here. So then you're going to write, I suppose in our case, we'll go to the next slide. So deciding whether or not to reject HO, well, we compared them, right? We compared the test statistic to the rejection point. Z is 2.2, and this is greater than the Z alpha of 1.645. Therefore, we reject HO that the mean is less than or equal to 25 in favor of the alternative hypothesis that the mean is greater than 25 at the 5% significance level. Okay, it's important that you write the alpha value, because if we change the alpha value, that might change the conclusion of our experiment. Okay, then you need to do step 5, which is interpret the statistical result. So you just need to write a sentence of what it actually means. So we conclude that the mean breaking point, breaking point or strength, I suppose, that the mean breaking point or mean breaking strength of the new bag exceeds 25 kilograms. Here's the interesting thing about hypothesis testing that's a big misconception in general. We can't actually say that we need a lot more data to say that the breaking point is 25 point whatever it was 575. All we can conclude is that it exceeds 25 kilograms. So it's subtle, but a lot of misconceptions about statistics actually is around this point here in hypothesis testing, because we use this all the time, like in the industry. Not your average person, but anyways, yeah, all we can say, it's important that it's reflected in your conclusion, is we can just say, hey, we exceed the null hypothesis, okay, at the 5% level. So there you have it. That's really hard. I recommend that you watch that again, because it's a lot of stuff to digest. So we're going to do another question. So different question, but this time it's going to be left-tailed. And I have the same setup as before, just different questions. So let's see. I'm promising you a less than example this time. So a management consulting company wishes to show that with its new billing system, the mean billing time is less than the standard 19.5 days in the current system. Their new billing system was tested 65 times with a mean billing time of 18 days with a standard deviation of 4.2. Test at a 1% level. Okay, so we know alpha is 1%. The mean billing time, the old system had 19.5 days. Now, when they did their sample of their new system, so that's X bar, it was tested 65 times, so N is 65, and they got a mean billing time of 18. Okay? Oh, and a standard deviation of 4.2 days. All right. So we're going to have to find Z alpha, and it's going to be 0.01. And we'll do this on the next slide, but I just wanted to write it here. I guess actually we'll write it here. Let's figure out our HO and our HA right now. So when you see a hypothesis testing question, you're going to go figure out the HO and the HA. Start with HA because it's easier to figure that out. What are they asking us for in this question? So they have this new billing system. Their new billing system was tested 65 times with a mean billing time of 18 days, tested at 1% level. So what are we going to want to show? That the mean billing time is less than, what's the old one? It's less than 19.5. So what would be the null hypothesis? Well, the null hypothesis, we can say mean is equal to 19.5, or we could say mean, what's the opposite here? So this is less than, greater than, or equal to 19.5. So that's what we will be showing. Perfect, that looks good. Let's go find. Oh, I said we would do it on the next page, and here we are. So you can transfer that over if you like. Step 2 is finding the significance level. So we need to go figure out what the picture is going to look like. I like to draw the picture here. You don't have to, but if we have, this is a left tail test. So it's going to be on the left-hand side. So this will be the reject HO region. And remember, I know it's a left tail test because the alternative hypothesis is less than or equal to a number. So it's at a 1% level. So we have 0.01% of the curve here and 99% to the right. So we're going to reverse look up 0.01 on these tables. No, 0.01 0.01. Get as close as we can. We got 0.0099, which is as close as we can get. So a negative 2.33. So since alpha is 0.01, the rejection point is negative Z alpha. Now the only reason it's negative is because we got negative 2.33. So you don't necessarily have to write that here, but just realize that as we're below the 50% mark, all our z-scores are negative because we are standard deviations below the mean. Okay. You also must write the statement in the payment time case, reject HO if the test statistic Z is less than negative 2.33. Perfect. I told you these would be long questions. Okay. Let's go ahead and find the value of the test statistic. So we're going to go plug it into our formula. It's just a standard, it's just the central limit theorem one. So what were the numbers? Well, X bar was 18. And the mean that was given was 19.5. And the standard deviation given was 4.2 divided by the square root of n, so square root of 65. Type that in on your calculator and you're going to get negative 2.88. So when we use the numbers given, we get a z-score of negative 2.88. Remember, you should draw the nice little picture. Draw it in here. Remember, if z is less than negative 2.33, so this value right here is z equals negative 2.33. So here we accept the HO if our z statistic lands in there. If it lands in there, we reject HO. So in this case, I might have the wrong number here. Yeah, this is a typo. This should be negative. There we go. Negative 2.88 is what we just found. So, in the payment time case, z is equal to negative 2.88, which is less than the z alpha score of negative 2.33. Therefore, we reject HO. We reject the HO that the mean time is greater than or equal to 19.5 in favor of alternative hypothesis that the mean time is less than 19.5 at the 1% level. Then write it in a sentence. So we can conclude that the mean bill time mean bill payment time maybe of the new system is less than 19.5 days. So that's good. Company gets its money sooner. That's really good. Perfect. So we're on the home stretch. We got one last hypothesis test to look at. I'm very sympathetic to you guys. I remember learning this the first time. It is some heavy stuff. The good news is that for the rest of the course, we're doing hypothesis testing. So, we'll build up the theory as we go. We're just looking at different kinds of hypothesis testing. The first week of it is generally the hardest. The good news is that the questions are fairly straightforward to recognize because you have an alpha value and then you basically have the three types, right? You got the greater than, or the less than, or the not equal to. So you watch for those words. Everything's on the formula sheet, and hopefully you can do those 5 steps. You'll sort of memorize those 5 steps and can actually get kind of fun after a while. So this one here goes like this. So a candy company markets a special 500-gram box of Valentine's Day chocolates to retail stores. Typically, each year sales grow 10%. So to prepare for the upcoming season, the company hires you to figure out whether or not they should prepare for a 10% increase in sales. You find last year the mean order was 300 boxes per store. Now you conduct a survey and you find that of the 100 stores sampled, the mean number of boxes they intend to order is 326 with a standard deviation of 40. So at the 5% level, should the candy manufacturer prepare 10% more boxes than last year? Oh, perfect. Let's take a look. So, why is this a two-tailed test or not equal to? Well, they either do or they don't. There's no less than or greater than if you read this question. Okay, so either we have the HO that the mean is equal to 330, which is 300 and then 10% more, or we have the HA that it does not equal 330, right? So we're not saying that it's going to be necessarily less or more. We're just interested in, should we prepare for the 10% increase or not? So either the mean is 330, which is 300 plus 10%, or it's not that. That's why it's a two-tailed test. Okay, so first step is always state those null hypothesis and alternative hypothesis. So the alternative is that the mean does not equal 330. And the null hypothesis is just that it does equal 330. Okay, the significance level, well, for a two-tailed test, we're doing it at the 5% level. Well, for a two-tailed test, we have a rejection region on both sides of the curve. So we're going to reject HO if we fall on the right-hand side, and we're going to reject HO if we fall on the left-hand side. So we take our 5% and we have to split it into two equal zones. So we have 2.5% on each side. So we start saying that we're going to calculate alpha divided by 2. So we set alpha equal to 0.05. And for the two-tailed test, we split up the alpha value in 2. So you get 2.5%, and you actually have 2 rejection regions, like I said. It all makes sense. Okay, so if you have 2 rejection regions, it's kind of weird, but you got 95% of the curve in the middle, and then you need to go find, well, what value over here gives you 0.025, or if you think about it on the other end, you'd be looking for 0.9725. Okay, so whichever one's more convenient to look up. Remember, the normal distribution is symmetrical, so whatever z-score this is, it's just going to be negative on this side. So we can go look it up. Okay, there it is. So 0.975, 0.975. There it is. So 1.96. 1.96. So on this side, it's z equals 1.96. Normal curve is symmetrical. To get negative 1.96 if you went and looked up the other one. So, you're going to say if z is greater than 1.96 or z is less than negative 1.96, then we reject HO. So remember, you must have that statement. So I tried to write some of the data out here. We're going to find our Z value. So the X bar that's given in the question is 326. That's the number of boxes that when they sampled the stores, they found they were going to order. Minus the population one, which is 330, divided by standard deviation of 40, divided by square root of n, and they sampled 100 stores. So when that's all said and done, you get a Z value of negative 1.00 exactly. So, are we going to reject HO or not? Well, in this case, we got Z equals negative 1.00, which is greater than the left side of it. So it's greater than the negative 1.96. And negative 1.00 is less than, ignore that little mark, less than 1.96. Therefore, we cannot reject HO equal 330 in favor of HA that it does not equal 330 at the 5% level. So just to be clear, if we go back to the picture here, we got a z-score of -1. Okay, so the picture really helps because we can see, well, -1 doesn't land here. It's not less than -1.96, and it's also not greater than 1.96. So when we're in the middle region, we accept HO. Now, it's tricky because you gotta interpret the results in English. So just remember that our HO was that the status quo, right? The status quo is that it's 10% more every year. So the status quo is that we'd have to prepare 330 boxes for each store. And we just found that we cannot reject HO, so we accepted HO. So that means that, I'm going to type this out actually, because it's a lot. Here we go. So we cannot conclude that the mean order quantity this year of the Valentine Day boxes at large retail stores will differ from 330 boxes. The manufacturer should expect demand to be 10% higher than last year. There. I was not about to write that out with my pen. There you have it. You can pause it there if you need. So it's just, if sigma is known, so if standard deviation is known, then we can use this z-score formula to test HO. So it's just the three things we did. So if HA is that mu is greater than the value, then we're looking for a critical rejection region of Z greater than Z alpha. If this is the case, then it's Z less than negative Z alpha, because this is a left tail test, will be on the left hand side of the table. And if it's not equal to, then it's more complicated because we need to check that Z is less than negative Z alpha divided by 2, or that Z is greater than Z alpha divided by 2. Okay, so there's two ways to reject it when it's a two-tailed test. That's a lot. I know that is a longer lesson than usual. Make sure that you're going on Moodle and doing the homeworks and asking questions. If you have them, I will make another video of extra questions that'll be really handy on top of the homework. And I recommend that you watch the parts again that you need to watch. Thanks for joining me this week. We'll see you next time. Bye-bye.